The photon leaves the laser at 10:47 p.m. on a Tuesday night in Canberra, Australia. It is May 2015, and the laboratory sits quiet, except for the hum of equipment and the soft clicking of computer keys. The photon, a single packet of light, begins its journey across an optical table roughly 1 meter long. At the speed of light, this journey should take approximately 3 nanoseconds, 3 billionths of a second. Less time than it takes for an electrical signal to travel from your brain to your fingertip. Less time than it takes for a hummingbird's wing to complete a single beat. But here is what the physicists in this laboratory are about to demonstrate. What their data will show when they finally publish their results. The choice they make at the end of this photon's journey, a choice made after the photon has already travelled most of its path, will determine how that photon behaved at the very beginning. The future, it seems, is reaching backward through time to shape the past. This is not science fiction. This is not philosophy. This is an experimental result, replicated and verified, published in one of the most respected physics journals in the world. And it is just one piece of a puzzle that has haunted quantum mechanics since its earliest days. A puzzle about the nature of reality, the meaning of observation, and whether the past is ever truly fixed. The story begins not in 2015, but decades earlier, in the mind of a physicist who was willing to take the strangest implications of quantum mechanics seriously. John Archibald Wheeler was not afraid of weird ideas. He had worked alongside Niels Bohr in Copenhagen, helped develop the theory of nuclear fission, contributed to the Manhattan Project, and coined terms that would become part of the scientific lexicon, including the phrase black hole. By the 1970s, Wheeler had turned his attention to the deepest mysteries of quantum physics, and he had designed a thought experiment that would challenge everything we thought we knew about cause and effect. To understand what Wheeler proposed, you first need to understand the double-slit experiment, perhaps the most famous demonstration in all of physics, and certainly the most troubling. Imagine a barrier with 2 narrow slits cut into it. Behind the barrier sits a detection screen that records where particles land. Now fire particles, electrons, photons, atoms, anything quantum, at the barrier one at a time. Each particle passes through the barrier and strikes the screen at a specific location, leaving a small mark. If you run this experiment many times and look at the pattern that builds up on the screen, you would expect to see 2 clusters of marks, one behind each slit. After all, each particle must go through one slit or the other, but that is not what happens. Instead, the screen displays an interference pattern, alternating bands of many hits and few hits, bright and dark, like ripples on a pond where 2 waves have crossed and reinforced or cancelled each other. This pattern is the unmistakable signature of wave behaviour. Somehow, each individual particle is interfering with itself, as if it went through both slits simultaneously. Here is where the strangeness deepens. Place a detector at one of the slits to determine which path the particle actually takes, and the interference pattern vanishes. The particles start behaving like particles again, landing in 2 clusters, one behind each slit. The mere act of measuring which path the particle takes, of gathering information about its route, destroys the wave-like behaviour. Stop measuring, and the interference returns. This is the central mystery of quantum mechanics, the puzzle that drove Einstein to argue with Bohr for decades, the riddle that prompted Richard Feynman to declare that nobody really understands quantum mechanics. When we don't look, particles behave like waves, existing in a superposition of multiple possibilities. When we look, they behave like particles committing to a single definite state. The act of observation seems to determine the nature of reality itself. Wheeler asked a simple question that cut to the heart of this mystery. What if we delay the choice of whether to observe until after the particle has already passed through the slits? Picture it this way. A photon approaches the double-slit barrier. If no detector is placed at either slit, the photon will pass through both slits simultaneously, existing in a superposition, interfering with itself, and landing on the screen in a position consistent with wave behaviour. If a detector is placed at one slit, the photon will go through only one slit, behaving as a particle. But what if we wait until after the photon has already passed through the barrier, after it has already committed to travelling through one slit or both, before we decide whether to make the measurement? Wheeler proposed setting up the experiment so that the choice of whether to observe the photon's path would be made at random, automatically, at the very last possible instant before detection. If reality operates the way our intuition suggests, if the past is fixed and causes precede effects, then this delayed choice should be irrelevant. The photon must have already decided, back at the barrier, whether to go through one slit or both. Our later choice of how to measure it cannot change what already happened. But quantum mechanics suggested otherwise, and Wheeler suspected that the experiment would show something deeply unsettling, that the delayed choice would somehow reach back in time, determining the photon's past behaviour retroactively. For decades, this remained a thought experiment. The technical challenges of building such a system were formidable. You needed sources capable of producing single photons on demand. You needed random number generators fast enough to make truly last-instant decisions. You needed detectors sensitive enough to register individual particles. You needed timing precision measured in nanoseconds or better. Throughout the 1980s and 1990s, physicists began building versions of the delayed choice experiment, each one adding new sophistication, each one confirming Wheeler's predictions. The most striking versions did not use double slits at all, but relied instead on devices called beam splitters, half-silvered mirrors that have a 50% chance of reflecting a photon and a 50% chance of letting it pass through. By arranging multiple beam splitters in sequence, experimenters could create setups equivalent to the double-slit experiment, with one crucial advantage. They could insert or remove the final beam splitter at will, effectively choosing at the last moment whether to measure which path the photon took. The results were consistent and disturbing. When the final beam splitter was inserted, meaning both paths were combined and which path information was erased, interference occurred. The photon had behaved like a wave, travelling both paths simultaneously. When the final beam splitter was removed, meaning the paths were kept separate and which path information was preserved, no interference appeared. The photon had behaved like a particle, travelling only one path. This remained true even when the choice was made after the photon had already entered the apparatus. The future measurement determined the past behaviour. But these early experiments, remarkable as they were, left room for certain objections. Perhaps the photon was somehow sensing the configuration of the apparatus ahead of time. Perhaps some subtle classical signal was leaking information backward. Perhaps the very setup of the experiment was constraining what could happen. To truly demonstrate Wheeler's vision, physicists needed to push the experiment further, to make the delay longer, the randomness more rigorous, and the conclusion more inescapable. This is what the Australian National University team set out to do in 2015. The laboratory sits in the physics building at ANU in Canberra, a low-slung structure surrounded by eucalyptus trees and positioned in a city known more for politics than for physics. The lead experimenter is Andrew Truscott, a soft-spoken man with the careful precision of someone accustomed to working with equipment that costs more than most houses. His team includes Roman Karkimov, who handles much of the day-to-day operation of the apparatus, and several graduate students whose careers will be built on this single result. They have chosen to work not with photons but with atoms, specifically helium atoms cooled to within a fraction of a degree above absolute zero. At these temperatures, helium enters a strange state of matter called a Bose-Einstein condensate, where individual atoms lose their separate identities and begin behaving as a single quantum entity. More importantly for this experiment, helium atoms are massive compared to photons. They travel slowly enough that their journey can be measured and manipulated with relative ease. The experimental setup uses laser beams to act as the beam splitters and mirrors. The cold helium atoms are released from a magnetic trap and begin to fall under gravity. As they fall, they encounter a first set of laser beams configured to split their quantum wave function into two paths, the atomic equivalent of passing through both slits simultaneously. The atoms then travel along these two paths for about a microsecond, an eternity by quantum standards, before potentially encountering a second set of laser beams that would recombine the paths. The key innovation is what happens during that microsecond of travel. The ANU team has set up a quantum random number generator, a device that produces genuinely random ones and zeros by measuring quantum fluctuations, and connected it to the second set of laser beams. The generator runs continuously, and at the moment when each atom needs to be measured, it produces a random bit. If the bit is 1, the second beam splitter activates, recombining the paths. If the bit is 0, the beam splitter stays off, keeping the paths separate. The choice is made only after the atom has already passed the first beam splitter. The atom has already begun its journey. already exists in a superposition of two paths, already has a past. And then the random number generator decides whether that past involved travelling both paths like a wave or only one path like a particle. Over the course of many nights, Truscott and his team run the experiment thousands of times. They analyse the patterns of atomic detections, comparing the cases where the second beam splitter was activated against the cases where it remained off. The mathematics is painstaking, but the conclusion is unambiguous. When the random number generator chose to activate the second beam splitter, recombining the paths and erasing which path information, the atoms showed interference. They had travelled both paths. When the generator chose to leave the beam splitter off, preserving which path information, no interference appeared. They had travelled only one path. The choice made after the atoms had already passed the first beam splitter determined what happened at that first beam splitter. Andrew Truscott, in interviews after the paper's publication, is careful with his words. He does not claim that the future literally causes the past in some science fiction sense. He does not suggest that you could use this phenomenon to send messages backward in time or to change history. The randomness of quantum mechanics prevents such possibilities, but he is equally careful not to minimize what the experiment shows. It proves that measurement is everything, he says. At the quantum level, reality does not exist if you're not looking at it. This statement sounds like mysticism, like something from a self-help book, rather than a physics journal. But it is a precise summary of what the Copenhagen interpretation of quantum mechanics has always claimed, now backed by an experiment that removes most of the remaining wiggle room. The Copenhagen interpretation, developed in the 1920s by Niels Bohr, Werner Heisenberg, and their colleagues, holds that quantum systems do not have definite properties until they are measured. Before measurement, a particle exists in a superposition of all possible states. The act of measurement collapses this superposition, forcing the particle to commit to a single definite outcome. In this view, asking what the particle was doing before measurement is meaningless. There was no definite was. The past becomes real only when the present forces it to. For decades, this interpretation troubled physicists who felt it was either incomplete or philosophically unacceptable. Einstein famously objected that God does not play dice with the universe. Others proposed alternative interpretations, hidden variable theories where the randomness conceals deeper deterministic processes, many worlds interpretations where every possible outcome occurs in branching parallel universes, pilot wave theories where particles are guided by invisible waves. Each interpretation makes the same predictions for experimental outcomes. They differ only in their philosophical commitments about what is really happening beneath the mathematics. The delayed choice experiment does not settle these debates, but it narrows the options. It shows that any interpretation of quantum mechanics must accommodate the fact that measurements made in the present can influence what we can say about the past. Whether you call this retrocausality, or delayed determination, or simply the non-existence of classical history at quantum scales, you must account for it. The year 2015 passes. The ANU paper is published in Nature Physics, generating headlines and debates. Most physicists nod and move on. The result is remarkable, but not unexpected. It confirms what quantum mechanics has always predicted. It is one more nail in the coffin of common-sense classical intuition, but the coffin was already well sealed. And yet some researchers are not satisfied. The ANU experiment, elegant as it is, involves atoms travelling over very short distances for very brief times. The delay between the first beam splitter and the final choice is measured in microseconds. What if you could stretch that delay? What if you could send photons across distances measured not in centimetres, but in kilometres? What if you could make the choice so late, and the journey so long, that any residual doubt about classical signals or advanced knowledge became completely untenable? This is the ambition that drives a group at the University of Vienna, led by a physicist named Anton Zeilinger, who has spent his career building ever more elaborate quantum optical experiments. Zeilinger is a white-bearded figure with a bemused expression, often photographed surrounded by complex arrays of mirrors and lasers that look like something from a heist movie. He has won the Wolf Prize and will later win the Nobel. His laboratory has demonstrated quantum teleportation, quantum entanglement across record distances, and numerous other feats that blur the line between physics and magic. Now, in the years following the ANU result, Zeelinger's group begins designing an experiment that will take Wheeler's delayed choice concept to its ultimate expression. The experiment they envision uses the phenomenon of quantum entanglement, the strange correlation between particles that Einstein called spooky action at distance. When two particles are entangled, measuring a property of one instantly determines the corresponding property of the other, regardless of the distance between them. This is not just a statistical correlation, it is a genuine quantum connection, verified by decades of experiments. The Vienna team plans to create pairs of entangled photons and send them along paths of very different lengths. One photon, call it the signal photon, travels a short path directly to a detector. The other photon, call it the idler photon, is sent on a long detour through optical fibers before arriving at its own detector. The key is that the measurement of the idler photon, the photon that arrives late, will determine whether the signal photon, which arrived early, exhibited particle-like or wave-like behavior. From the signal photon's perspective, its journey is complete and recorded before the idler photon even finishes travelling. Its fate should be sealed, its past should be fixed, and yet the delayed measurement of the idler photon will reach back and determine what that past was. The group publishes preliminary results in 2017, and then refines the experiment over the following years. The version that appears in 2019 involves fibre optic cables stretched across the Vienna metropolitan area, with photons travelling paths that differ in length by several hundred metres. The delay between the signal photon's detection and the idler photon's measurement is measured in microseconds at minimum, and the physical separation during this delay ensures that no speed of light signal could possibly connect the two events. The random number generator that determines the final measurement setting is based on cosmic microwave background radiation, light from the early universe that has been travelling for over 13 billion years. This is not a gimmick, it is a profound choice. By using randomness derived from the distant past, the experimenters ensure that no local hidden variable could have anticipated the measurement choice. The decision of how to measure the idler photon is determined by fluctuations that occurred when the universe was a fraction of its current age, long before Earth existed, long before the concept of a laboratory was meaningful, and still the results show the same pattern. The measurement of the late arriving idler photon determines whether the early arriving signal photon displayed interference or not. The cosmic random number generator makes its choice effectively billions of years ago, but from the perspective of the experimental timeline, the choice arrives late, after the signal photon has already completed its journey. The past, once again, is shaped by decisions made in what we would normally call the future. The physicists in Vienna published their results with the same careful qualifications that Truscott used in Australia. They do not claim to have broken causality. They do not suggest that you can send information backward in time. The randomness inherent in quantum mechanics still prevents any usable signal from travelling from future to past. But they do make clear that our ordinary conception of time, in which the past is fixed and the future is open, does not apply at the quantum level. What then does apply? This is the question that haunts the late hours in laboratories from Canberra to Vienna to Boston to Tokyo. It is the question that fills conference sessions and journal articles and late-night arguments over beer. The experimental results are not in dispute. The mathematics predicting them is not in doubt. What remains uncertain is the interpretation, the story we tell ourselves about what is really happening when a measurement made in the present determines a particle's past. One possibility is that retrocausality is real, at least at the quantum level. Perhaps causes can follow effects. Perhaps the future genuinely influences the past, and our intuition about the direction of time is simply wrong. This view has defenders among serious physicists, though it remains a minority position. The challenge is that retrocausality, if taken literally, seems to threaten the logical consistency of the universe. If the future can cause the past, what prevents paradoxes? What prevents you from creating a situation where event A causes event B, and event B prevents event A from happening? The standard answer is that quantum mechanics contains built-in safeguards against such paradoxes. The fundamental randomness of quantum outcomes means that you can never control precisely what information travels backward. You cannot use entanglement to send a message faster than light, and you cannot use delayed choice experiments to change the past in any useful way. The retrocausal influence exists, but it is always hidden beneath a veil of noise that prevents exploitation. Another possibility is that there is no backward causation at all. that the delayed choice experiment simply reveals that the past does not exist in the way we imagine. In this view, asking what the photon really did before measurement is asking a meaningless question. There is no fact of the matter about the photon's history until that history is relevant to a present measurement. The past is not a fixed ledger of events, but a probability space that collapses into definiteness only when queried. This interpretation is philosophically vertiginous. It suggests that the universe does not maintain a continuous record of events, but generates history retrospectively, on demand, in response to present observations. The past becomes a kind of story that the universe tells to remain consistent with its present state, not a sequence of events that cause that state. Still, a third possibility involves the many worlds interpretation, where every quantum outcome occurs in a branching universe and no collapse ever happens. In this view, the delayed choice experiment does not show retrocausality, but merely reveals our particular location in the vast tree of parallel realities. The photon went through both slits and one slit, and neither slit and every other possibility. We simply find ourselves in a branch where a particular outcome was observed, and other versions of us find themselves in branches with different outcomes. Each interpretation has its advocates, each has its puzzles. None has been experimentally distinguished from the others, because they all predict the same quantum mechanical results. The choice between them is, for now, a matter of philosophical taste, of which mysteries you find most tolerable. But what is not a matter of taste is the experimental fact. In laboratories around the world, physicists have demonstrated that quantum systems do not have fixed histories independent of observation. The past, at least for individual particles, is not written until it is read. Consider what this means for the nature of reality. We tend to think of the universe as a vast machine, ticking forward in time according to fixed laws. The present moment is the leading edge of a cone of light spreading into the future. Everything behind that edge is the past, fixed and immutable. History happened. The dinosaurs either went extinct or they didn't. Caesar either crossed the Rubicon or he didn't. The photon either went through the left slit or the right slit or both. But at the quantum level, this picture breaks down. The photon's history is not written until a measurement forces it to be written, and that measurement can come late, nanoseconds late, microseconds late, perhaps someday seconds or minutes or longer. Until the measurement, there is no fact about which path the photon took, because paths themselves are quantum mechanical variables subject to superposition. Does this quantum strangeness extend to larger objects, to cats and tables and planets? This is the measurement problem, the deepest puzzle in quantum mechanics. Quantum mechanics describes electrons and photons and atoms with exquisite precision, predicting their behavior to more decimal places than any theory in history. But it also predicts that these particles exist in superpositions of multiple states until measured. If quantum mechanics is universal, why don't chairs exist in superpositions? Why don't people? One answer is decoherence, the process by which quantum superpositions are rapidly destroyed when systems interact with their environments. A single photon in vacuum can maintain its superposition because it interacts with nothing. An atom in a warm laboratory begins to interact with air molecules, thermal photons, and electromagnetic fields almost immediately. These interactions effectively measure the atom, collapsing its superposition and forcing it into classical definiteness. Large objects decohere so quickly that their quantum behavior is impossible to observe. But decoherence doesn't make quantum strangeness go away, it just hides it. The superpositions aren't truly destroyed. They spread outward into the environment, becoming entangled with ever more particles, becoming unmeasurable in practice but still present in principle. The many worlds interpretation suggests that decoherence is simply the process by which branches of the universal wave function stop interfering with each other. Not a collapse, but a separation. And if superposition persists, even in hidden form, then the lessons of the delayed choice experiment persist too. The history of any system at bottom is not fixed until it is observed. The observations that fix history can come late. The story of the past is written from the perspective of the present. The implications fan outward, touching philosophy and theology and our deepest intuitions about what it means to exist in time. In a universe where the past is not fixed until observed, what is history? What is memory? What is causation? We experience the past as immutable, as something that happened, but perhaps this experience is itself a kind of observation, a continuous process of querying the universe for information about what preceded the present moment. Each query collapses possibilities into actualities. Each memory creates the past it remembers. This is not solipsism. The universe does not care whether humans observe it. But it may be something stranger, a reality that generates itself recursively, defining each moment in terms of the moments that follow. The physicists do not claim to have answered these questions. Their papers are modest in scope, careful in language, focused on specific experimental protocols and statistical analyses, but the data they have gathered sits in their laboratory notebooks and computer files like a small explosive charge, waiting for someone to fully appreciate its detonative potential. What they have shown is that John Wheeler's thought experiment, born in the 1970s from pure philosophical speculation, describes the actual behaviour of matter and light. The delayed choice is not a paradox to be resolved, but a fact to be accepted. Quantum systems do not commit to definite histories until those histories are measured. The measurement can come late, and when it does, it reaches backward, not in the sense of sending signals or changing outcomes that have already been recorded, but in the sense of determining what those outcomes were in the first place. The photon that left the laser at 10:47 p.m. in Canberra did not know where it was going until it arrived, and perhaps, in some deep sense, it did not know where it had been until someone asked. The night deepens over the Australian National University. The eucalyptus trees outside the physics building sway in a light breeze. Inside, the optical table holds its maze of mirrors and lasers, now silent, the day's experiments complete. The data has been recorded, analysed and added to the growing body of evidence that reality at its most fundamental level does not behave the way we expect. Tomorrow there will be more experiments, more photons will be produced, more choices will be delayed, more measurements will be made. The universe will continue to refuse to be pinned down, to insist on its quantum strangeness, to demonstrate over and over that the question "what happened?" has no answer. Independent of the question "when did you look?" And in Vienna, another team is already planning the next generation of tests. They are thinking about longer delays, larger distances, more exotic configurations. They are wondering whether there are limits to how far the delayed choice effect can be pushed, whether at some scale the universe will finally insist on a classical past, or whether, all the way down, reality is constructed not from what was, but from what is observed to have been. The questions stretch forward into the future of physics, carrying with them the unsettling possibility that the past is never as past as we thought. The morning arrives in Vienna with the particular grey light of late autumn, the kind of diffused luminescence that seems to come from everywhere and nowhere at once, filtering through clouds that have settled over the city like a blanket. In a laboratory at the Austrian Academy of Sciences, a researcher named Philip Walter reviews the data from his team's latest experimental run. The numbers on his screen tell a story that would have seemed impossible a century ago, a story about particles that seem to choose their past after their future has already begun to unfold. Walter's team has been pushing the boundaries of what Wheeler imagined. Where the Canberra experiments tested the delayed choice phenomenon over distances measured in meters, the Vienna group has begun thinking in terms of kilometers, of satellite links, of the vast spaces between ground stations and orbiting laboratories. They understand that each incremental expansion of scale is not merely a technical achievement, but a philosophical probe, a way of asking the universe just how committed it is to this strange backward-looking indeterminacy. The history of this Vienna research group stretches back through decades of quantum optical innovation. It was here that some of the first practical demonstrations of quantum entanglement were performed, here that the foundations for quantum cryptography were laid, here that the bizarre predictions of Bell's theorem were tested with ever-increasing precision. The laboratory is a cathedral of coherent light, a space where photons are not merely illumination, but the very substance of inquiry. And now the cathedral has become a workshop for exploring the malleability of the past. The 2019 experiments that emerged from this setting built upon the Canberra results, but introduced new layers of complexity. The Vienna team was interested in something called entanglement swapping, a protocol in which the correlations between particles can be transferred, like a baton passed from runner to runner, without any direct interaction between the particles that end up entangled. In ordinary entanglement swapping, Two pairs of particles are created, and then measurements on one particle from each pair can project the remaining two particles into an entangled state, even though those particles never interacted directly. The Vienna group's insight was to delay the measurement that determines whether entanglement swapping occurs. They created their particle pairs and allowed one member of each pair to travel to separate detection stations. Then, after these particles had already been detected, they made the choice of whether to perform the measurement that would swap the entanglement. The results were striking. The choice made after the fact determined whether the previously detected particles exhibited entanglement correlations or not. To understand why this matters, consider what entanglement means. Two entangled particles share quantum correlations that cannot be explained by any local hidden variable. This is the content of Bell's theorem, one of the most tested and verified results in all of physics. When particles are entangled, measurements on one particle are correlated with measurements on the other, in ways that exceed what any classical, predetermined correlation could achieve. The correlations are not merely statistical patterns, they are signatures of a quantum connection that transcends ordinary notions of cause and effect. In the Vienna experiment, the question of whether particles were entangled or not seemed to be determined retroactively. The particles were detected, the data was recorded, and then, only after, the experimenters made a choice that determined what kind of correlations existed in the already recorded data. It was as if the experimenter's decision reached back in time and wrote itself into the history of particles that had already completed their journeys. The laboratory notebooks from these experiments contain meticulously recorded timestamps. Each event, the creation of particle pairs, the detection of individual photons, the random choices generated by the quantum random number generators, the final measurements that determine the nature of the correlations, is logged with nanosecond precision. The temporal sequence is unambiguous. The detection happens first. The choice happens second. And yet the choice determines what the detection reveals. Philip Walter speaks about these results with the careful precision of a scientist who knows he is treading on philosophically treacherous ground. He does not claim to have proven that the future causes the past. He does not claim to have built a time machine. What he claims is more modest, and in its modesty, more disturbing. He claims to have shown that the question of whether particles are entangled has no answer until someone asks it, and that this asking can be delayed arbitrarily, long past the point where classical intuition insists the answer should have been fixed. The theoretical framework that supports these experiments draws on some of the deepest work in quantum foundations. The idea of entanglement swapping was first proposed in the early 1990s, building on the growing understanding of quantum information that was transforming the field. The delayed choice version was suggested as a way to probe the temporal structure of quantum correlations, and now, 3 decades later, the technology has caught up to the theory. The photon sources used in the Vienna experiments are marvels of engineering. They employ a process called spontaneous parametric down conversion, in which a single high-energy photon passing through a nonlinear crystal spontaneously splits into 2 lower-energy photons. These daughter photons are created in an entangled state, their polarizations correlated in ways that cannot be explained classically. The process is probabilistic. Most high-energy photons pass through the crystal unchanged, but when it works, it produces pairs of particles that share a quantum bond across whatever distance separates them. The detection systems are equally sophisticated. Single photon avalanche diodes can register the arrival of individual quanta of light with timing resolutions measured in picoseconds. Electronic coincidence circuits can identify which photons belong to which pairs, sorting through the random noise of background events to find the correlated signals that carry quantum information, and quantum random number generators, devices that exploit the fundamental randomness of quantum mechanics, ensure that the choices made by the experimenters are genuinely unpredictable, not determined by any hidden pattern that the photons might have anticipated. This last point is crucial. If the photons somehow knew in advance what choice the experimenter would make, they could behave accordingly, and the experiment would prove nothing about the nature of time or causation. The quantum random number generators close this loophole. They ensure that the choice is made by a quantum process that has no predetermined outcome, that the universe itself does not know what will be chosen until the moment of choosing. And yet the results come out exactly as if the photons did know. They exhibit the correlations appropriate to the choice that will be made, not some average or mixture of possible choices. The universe, it seems, writes its history in response to questions that have not yet been asked. The philosophical literature on these experiments has grown thick with competing interpretations. Some physicists embrace the retrocausal reading directly, arguing that quantum mechanics requires us to accept that influences can travel backward in time as easily as forward. Others prefer to speak of atemporal correlations, insisting that the very notion of temporal order is an approximation that breaks down in quantum contexts. Still others invoke the many worlds interpretation, in which every possible outcome occurs in some branch of a constantly splitting reality, and the experimenter's choice merely determines which branch she finds herself in. None of these interpretations is fully satisfactory. Each resolves certain puzzles while creating others. The retrocausal interpretation seems to violate our deepest intuitions about causation, yet it has the virtue of simplicity. The atemporal interpretation preserves the direction of time, but at the cost of making quantum correlations utterly mysterious, unexplained coincidences. The many worlds interpretation preserves both temporal order and determinism, but at the cost of an infinitely bloated ontology, a universe constantly spawning copies of itself. What unites all these interpretations is an acknowledgement that the experiments are real, that the data cannot be dismissed or explained away. Whatever the photons are doing, they are doing it consistently, reliably, in every laboratory that has tested the delayed choice phenomenon. The effect is not a statistical fluke or an artifact of poor experimental design. It is a feature of the quantum world. The Vienna team's work has inspired a new generation of experiments. Proposals now circulate for satellite-based delayed choice tests, in which the distance between creation and measurement will be measured in thousands of kilometres, the delay in milliseconds, or even seconds. The International Space Station has already hosted quantum experiments, and the Chinese Misyus satellite has demonstrated quantum communication over continental distances. It is only a matter of time before delayed choice experiments join this roster of space-based quantum tests. The motivation for such experiments is not merely to confirm what has already been shown, but to search for limits. At what scale, if any, does the delayed choice effect break down? Is there a distance beyond which the universe insists on definite histories, a delay beyond which the past solidifies and refuses to be written retroactively? No one knows. The theoretical frameworks that describe quantum mechanics do not predict any such limit, but theories have been wrong before. The only way to know for certain is to test. And so, the work continues. In Vienna, in Canberra, in laboratories across Europe and Asia and the Americas, physicists prepare their sources and align their detectors and program their random number generators. They are cartographers mapping the boundaries of a strange territory, explorers probing the limits of a reality that does not behave the way anyone expected. The city of Vienna itself seems an appropriate setting for such work. This is the city of Schrödinger, who first wrote down the equation that describes the evolution of quantum states. This is the city of Boltzmann, who founded statistical mechanics and fought bitter battles over the reality of atoms. The intellectual tradition runs deep here, embedded in the stone facades of the universities, the cafes where physicists have debated for generations, the lecture halls where the quantum revolution first took shape. Walking through the streets of Vienna's first district, past the Hofburg Palace and the Gothic spire of St. Stephen's Cathedral, one can imagine the conversations that must have taken place in the 1920s and 1930s when Heisenberg and Bohr and Pauli were regular visitors, when the foundations of quantum mechanics were still being laid. Those conversations have never really ended. They continue in the laboratories and seminar rooms and conference halls, carried forward by new generations of physicists who have inherited both the mathematical tools and the philosophical puzzles of their predecessors. The question that John Wheeler asked in the 1970s, does the past have a definite history before it is observed, remains open. The experiments have not answered it so much as sharpened it, transforming a speculative thought experiment into a precise empirical question. And the answer that the experiments suggest is disturbing. No, the past does not have a definite history before it is observed. The observation creates the history it observes. This is not the same as saying that the past does not exist, or that reality is merely subjective. The experiments are exquisitely objective. Any competent physicist can replicate them, and the results do not depend on who performs the measurements or what they expect to find. What the experiments suggest is something more subtle, that the objective reality of the past is not a fixed stage on which events have already unfolded, but a dynamic process in which the present is constantly completing the historical record. There is a word that physicists sometimes use to describe this situation: contextuality. Quantum mechanics is contextual because the outcomes of measurements depend not just on the properties being measured, but on the entire experimental context, including measurements that have not yet been made. The delayed choice experiments are extreme examples of contextuality, in which the relevant context extends backward in time, reaching from the present moment into what we ordinarily think of as the settled past. The implications extend beyond physics proper. Philosophers of time have long debated whether the past, present and future are equally real, a view called eternalism, or whether only the present is real, with the past having ceased to exist and the future not yet existing, a view called presentism. The delayed choice experiments seem to complicate both positions. If the past is not fixed until observed, then it is neither fully real in the eternalist sense nor fully unreal in the presentist sense. It is something in between, a realm of potentiality waiting to be actualized by future observations. This has led some philosophers to propose novel accounts of temporal reality, in which the past is not a static record but an evolving network of possibilities that gradually consolidates as information propagates through the universe. On this view, the past is real but not complete, always subject to further specification by observations that have not yet occurred. The present is not a knife edge between past and future, but a dynamic interface where reality is being constructed. Such ideas remain speculative, more philosophy than physics, but they draw their inspiration from the experimental results, from the hard data that shows photons refusing to commit to definite paths until someone looks. The experiments anchor the speculation, preventing it from floating off into pure abstraction. Whatever account of time we ultimately accept, it must accommodate what happens in the laboratories of Canberra and Vienna. The day progresses in the Austrian capital. Clouds part briefly to admit shafts of sunlight that illuminate the baroque facades, then close again. In the laboratory, the optical systems hum with contained energy, ready for the next round of tests. The researchers move through their protocols with practiced efficiency, aligning mirrors, checking detectors, verifying that the random number generators are functioning properly. Each experimental run is a dialogue with the universe, a question posed in the language of photons and answered in the language of correlations. The questions are always the same. Which path did the particle take? Were the photons entangled or not? And the answers always depend on when and how the question is asked. There is a humility in this work, a recognition that the universe is stranger than human intuition can easily accommodate. The physicists do not pretend to have solved the puzzle of quantum measurement or resolved the interpretation of quantum mechanics. They know that their experiments raise as many questions as they answer, but they also know that the experiments are valuable precisely because of the questions they raise, because they force us to confront the inadequacy of our classical concepts when applied to the quantum realm. The history of physics is full of such moments of confrontation. The discovery of special relativity forced physicists to abandon absolute simultaneity. The discovery of general relativity forced them to reconceptualize gravity as space-time curvature. The development of quantum mechanics forced them to accept intrinsic randomness and the limits of classical determinism. Each revolution required not just new equations, but new ways of thinking, new conceptual frameworks for making sense of mathematical structures that did not fit into existing categories. The delayed choice experiments may be heralds of another such revolution, or they may be curiosities that fit neatly into existing frameworks once those frameworks are properly understood. No one knows yet. The work of understanding is ongoing, and the experiments are data points in a much larger investigation. What is certain is that the experiments cannot be ignored. They are not speculative proposals or theoretical predictions awaiting confirmation. They are facts, recorded in laboratory notebooks, published in peer-reviewed journals, replicated by independent research groups. The photons behaved as they behaved. The correlations appeared as they appeared. The data is what it is. And what the data shows is a universe that does not fix its past until asked. A universe in which delayed choices reach backward, not to change recorded outcomes, but to determine what those outcomes were in the first place. A universe in which the distinction between past and present is not as absolute as everyday experience suggests. The evening descends over Vienna, and the lights come on in the cafes and apartments. The Danube reflects the city's glow as it flows past, carrying water that has travelled through mountains and valleys, through countries and centuries. Time flows like the river, or so we think, always forward, never back, carrying the past away like debris on the current. But the photons in the laboratory tell a different story. They whisper that time may not flow at all, that the river metaphor may be an illusion born of classical intuition, applied inappropriately to quantum reality. They suggest that the universe is woven from a fabric stranger than rivers or flows, a fabric in which past and present and future are entangled in ways we are only beginning to understand. The experiments continue, the questions multiply, and somewhere, in the quantum darkness where photons exist in superposition, the answers wait, not fixed, not determined, but hovering in potential, ready to be called into being by the observations that will shape them into definite form. The story of the past, it turns out, is still being written, and the author is not the past itself, but the present that reaches back to read it. The morning light in Canberra arrives with the particular clarity of the Australian Capital Territory, a sharpness in the air that seems to promise precision, exactitude, the kind of atmospheric conditions that make physicists slightly more optimistic about their calibrations. At the Australian National University, in a building that houses some of the most sophisticated quantum optics equipment in the Southern Hemisphere, a different team has been wrestling with the same fundamental questions that occupied the Vienna researchers, but with their own experimental architecture, their own approach to interrogating the quantum realm. The year is 2015, and Andrew Truscott's research group has been preparing an experiment that will take Wheeler's delayed choice thought experiment and realise it in a form even closer to his original conception. Where the Vienna experiments used photons and the subtle dance of entanglement swapping, the Canberra team has chosen to work with something heavier, slower, more amenable to certain kinds of manipulation. Atoms of helium, cooled to temperatures so close to absolute zero that they become something called a Bose-Einstein condensate, a state of matter in which quantum effects that are usually invisible become macroscopic, tangible, almost graspable. The choice of helium atoms rather than photons is deliberate and strategic. Photons move at the speed of light, which makes timing extremely challenging. Events that need to be separated by meaningful intervals must be separated by significant distances, and even then, the margins are razor thin. Atoms, by contrast, move slowly, slow enough that the timeline of the experiment can be stretched out, made more accessible to human intervention. The delayed choice can be delayed by microseconds rather than nanoseconds, giving the experimenters more control over the precise moment when the measurement configuration is determined. But there is another reason for the choice of atoms, one that cuts closer to the philosophical heart of the matter. Photons are pure quanta of electromagnetic radiation, massless and in some sense ethereal. They have long been the workhorses of quantum experiments precisely because they are relatively easy to produce, manipulate and detect. But their very simplicity has sometimes made it tempting to dismiss quantum weirdness as something peculiar to light, something that might not apply to real matter, with rest mass and more substance. By demonstrating delayed choice effects with massive particles, atoms with their protons and neutrons and electrons, their nuclei and electron clouds, their unmistakable materiality, the Canberra team could show that the phenomenon is not a quirk of photonics, but a fundamental feature of quantum mechanics itself. The experimental setup begins with a cloud of helium atoms trapped and cooled in a magneto-optical trap, held in place by intersecting laser beams that push against the atom's thermal motion, bleeding away energy until the cloud's temperature drops below 1 microkelvin. At these temperatures, the atoms are moving so slowly that their quantum wavelengths become significant, comparable to the spacing between atoms in the cloud. The individual particles begin to lose their distinctness, their wave functions overlapping and merging into a collective quantum state. From this cloud, the experimenters extract single atoms, releasing them one at a time to fall under the influence of gravity. As each atom falls, it passes through a pair of laser beams arranged to function as a beam splitter, the atomic equivalent of the half-silvered mirror in the photon experiments. The beam splitter puts the atom into a superposition of two momentum states, effectively splitting its quantum trajectory into two paths. In the language of the experiment, one path carries the atom in the original direction of fall, while the other carries it at an angle, deflected by the momentum imparted by the laser light. The atom falls, or rather, the superposition of the atom falls, following both paths simultaneously in the quantum sense, the wave function spreading through space like a wave passing through two slits. And then, at a predetermined point in the fall, the experimenters face the choice that lies at the heart of the experiment, whether to recombine the paths or not. If they choose to recombine, if they activate a second set of laser beams that serve as another beam splitter, the two paths interfere, and the atom shows interference patterns characteristic of wave behaviour. If they choose not to recombine, if they leave the second beam splitter off, the atom can be detected on one path or the other, showing particle behaviour. So far, this is exactly analogous to the photon experiments, the same complementarity between wave and particle, the same dependence of behaviour on measurement configuration. But the critical innovation in the Canberra experiment is the timing of this choice. The decision whether to activate the second beam splitter is made after the atom has already passed through the first beam splitter, after it has already been put into superposition, after it has already begun to follow both paths. The choice is delayed, made by a random number generator in the last moments before the atom reaches the detection region. By the time the random number is generated and the beam splitter is either activated or not, the atom has been travelling in superposition for a significant fraction of the total experimental duration. The technical challenges of implementing this delayed choice are formidable. The timing must be precise to microseconds. The random number generator must be truly random, not pseudo-random, to close the loophole that the choice might somehow be predetermined and communicated backward through some unknown mechanism. The activation of the beam splitter must be fast enough that there is no possibility of information about the choice travelling at the speed of light to influence the atom's behaviour at the first beam splitter. Every aspect of the experiment must be designed to ensure that the choice is genuinely delayed, genuinely random, genuinely incapable of influencing the past through any known physical mechanism. Andrew Truscott is a careful man, the kind of physicist who checks calibrations twice and thinks about systematic errors even in his sleep. He knows that any experiment claiming to show something as strange as apparent retrocausality will be scrutinised intensely, that skeptics will look for every possible loophole, every alternative explanation. The experiment must be designed not just to work, but to be bulletproof against objections. The results, when they come, are unambiguous. When the random number generator chooses to activate the second beam splitter, the atoms show interference, wave behaviour. When it chooses not to activate the beam splitter, the atoms show particle behaviour, detected on one path or the other. The correlations are strong, the statistics are clear, the conclusion is inescapable. The behaviour of the atom appears to depend on a choice that is made after the atom has already passed through the first beam splitter. Let that sink in for a moment. The atom passes through the beam splitter and enters a superposition of two paths. While it is travelling, while it is in some sense already committed to its quantum state, a random number is generated and a choice is made about how to measure it. And then, when the measurement is performed, the atom's behaviour is consistent with that later choice having always been the case. If the second beam splitter is present, the atom behaves as though it travelled both paths, as a wave. If the second beam splitter is absent, the atom behaves as though it travelled one path, as a particle. The future measurement seems to reach back and determine what happened in the past. Truscott and his colleagues published their results in Nature Physics, one of the most prestigious journals in the field. The paper is titled with characteristic scientific understatement, but its implications are anything but understated. The experiment demonstrates that Wheeler's thought experiment, proposed decades earlier as a philosophical puzzle, is experimentally real. The delayed choice affects not just photons, but massive atoms, not just ethereal quanta of light, but genuine pieces of matter. Whatever is happening in these experiments, it is happening to the stuff the world is made of. The scientific community responds with a mixture of fascination and caution that characterises mature physics. The results are accepted, the experiment is well designed, the data is clean, the conclusions follow from the evidence. But the interpretation remains contested, debated, uncertain. What does it mean for a measurement to influence the past? What does it mean for an atom to not have a definite history until that history is observed? Some physicists reach for the language of many worlds interpretation, suggesting that the atom follows both paths in all cases and that the measurement simply determines which branch of the universal wave function the observer finds themselves in. In this view, there is no retrocausality, no reaching back into the past, just a vast proliferation of equally real branches, each containing a different outcome. The delayed choice does not change the past, it simply reveals which past is the one we experience. Others prefer the consistent histories approach, which holds that asking about the atom's path before the measurement configuration is determined is simply a meaningless question. The path is not undefined in the sense of being fuzzy or uncertain. It is undefined in the sense of not being a legitimate thing to ask about. The question, which path did the atom take, has no answer, not because we lack information, but because the question itself presupposes a classical definiteness that does not apply to quantum systems. Still others lean toward more radical interpretations, transactional or retrocausal interpretations that take seriously the idea that influences can propagate backward in time. In these frameworks, the delayed choice experiments are not puzzles to be explained away, but clues to a deeper structure of reality, one in which the future and the past are linked in ways that classical physics could never accommodate. The debates among physicists are not mere academic exercises, not angels on pinheads disputes with no connection to empirical reality. They are genuine struggles to make sense of data that does not fit easily into any existing framework. The experiments have been done, the results are in, and now the hard work of interpretation must proceed. What does it mean? What is the universe telling us about its own structure? These are the questions that keep theoretical physicists awake at night, scribbling on whiteboards, arguing in seminar rooms, trying to construct conceptual frameworks that can accommodate the experimental facts without doing violence to logic or common sense. 4 years pass, and the experimental frontier advances again. In Vienna, where Zeilinger's group has already achieved so much, a new generation of experiments begins to take shape. The goal this time is even more ambitious: to push the delayed choice paradigm to its logical extreme, to create situations in which the causal structure of the experiment is as scrambled as quantum mechanics allows. The 2019 Vienna experiment is a masterpiece of quantum engineering, building on everything that has been learned in the preceding decades. It involves not just delayed choice, but something more subtle: indefinite causal order. In this experiment, the very sequence of events, which operation is performed first, which second, is placed into quantum superposition. The experiment does not just delay the choice about how to measure, it creates a situation in which the order of measurements is itself undefined until a final measurement determines it. This is genuinely mind-bending territory, the kind of physics that makes even experienced quantum physicists reach for analogies that they know are inadequate. Imagine a conversation in which the question is asked after the answer is given, but also the answer is given after the question is asked, and both of these happen simultaneously, or neither, or both in superposition. The language breaks down because language is built for a world with definite causal order, a world in which causes precede effects, and effects follow causes. The 2019 experiment steps outside that world, into a regime where the rules are different. The technical apparatus required for this experiment is astonishing in its complexity. Photon pairs are generated and sent through quantum switches, devices that can route photons through different paths depending on quantum states of control photons. These switches are arranged so that the order in which operations are performed on a photon depends on the state of another photon, which is itself in superposition. The result is a situation in which photon A is operated on before photon B, and photon B is operated on before photon A simultaneously, or rather, in superposition of these two causal orderings. The measurements performed in this configuration show correlations that cannot be explained by any definite causal order. The statistics of the outcomes are inconsistent with first A, then B, and also inconsistent with first B, then A. The only way to explain the data is to accept that the causal order itself is indefinite, that the photons exist in a superposition of different causal histories until a measurement collapses that superposition into a definite sequence. The implications of this result go beyond the already strange implications of ordinary delayed choice experiments. If the order of events can be put into superposition, then the concept of before and after becomes contingent, dependent on measurement, not fixed by the structure of space-time itself. The flow of time, that river that seems so unidirectional, so absolute, becomes a quantum variable subject to the same superposition and entanglement that govern particle positions and momenta. This is not time travel in the science fiction sense. No messages are sent backward, no paradoxes created, no grandfather killed. The information-theoretic constraints that prevent paradoxes in closed time-like curves also prevent them here. But what these experiments show is that time's apparent unidirectionality, its arrow pointing always from past to future, may be an emergent feature of the classical world rather than a fundamental feature of quantum reality. At the deepest level, time may be stranger than we ever imagined. Not a river flowing from past to future, but something more like a quantum web, with causal connections running in directions that our classical intuitions cannot easily represent. The cafe where Wheeler first proposed his thought experiment is long gone, but in its place, other cafes serve other physicists, who drink their coffee and argue about interpretations just as their predecessors did. The questions have not been answered, only sharpened. The experiments have not resolved the mysteries, only deepened them. But this is how science progresses, not by eliminating wonder, but by localizing it, by identifying precisely where the strangeness lies, by ruling out some possibilities and leaving others standing. What the experiments have ruled out is any interpretation that takes the past to be fully determined before observation. The classical picture of a universe unfolding from initial conditions, with each moment determined by the moment before, cannot survive contact with these results. Whatever is happening in the quantum realm, it is not the clockwork determinism of Laplace's demon, that imaginary intelligence who could predict the entire future of the universe from perfect knowledge of its present state. The demon would need to know not just the present state, but also the future choices of experimenters, and those choices are not determined until they are made. What the experiments have not ruled out is a bewildering array of possible interpretations, each with its own virtues and its own costs. Many worlds preserves determinism at the cost of an infinity of parallel realities. Consistent histories preserves a kind of logic at the cost of prohibiting certain questions. Transactional interpretations allow backward-in-time influences at the cost of violating the causal intuitions that serve us so well in everyday life. No interpretation is forced by the data. All are consistent with it. The choice among them is partly empirical, partly aesthetic, partly a matter of which foundational principles one is willing to sacrifice. The laboratories where these experiments are performed are quiet places, despite their revolutionary implications. The hum of vacuum pumps, the click of photon detectors, the soft glow of control room monitors, these are the sounds and sights of cutting-edge physics, the environment in which humanity's deepest questions about the nature of reality are being explored. The researchers who work there are not mystics or philosophers, but hard-nosed empiricists, people who trust data over speculation and who subject their results to the most rigorous statistical analysis before drawing any conclusions. And yet, the conclusions they draw challenge the deepest assumptions of the scientific worldview. The idea that the past is fixed and the future is open, that everything that has happened is determined and only the future remains to be decided, is so fundamental to our understanding of time that we rarely even notice we hold it. It is built into our language, our logic, our planning for the future, our memories of the past. And yet the delayed choice experiments suggest that this assumption may be wrong, or at least incomplete, or at least inapplicable to quantum systems in ways that matter. The helium atoms in Canberra and the photons in Vienna are messengers from a deeper reality, ambassadors from the quantum realm where the rules are different. They do not speak in words, of course, but in statistics, in the correlations between measurements, in the patterns that emerge from many repetitions of the same experiment. And what they say, translated from the language of data into the language of concepts, is this: your past is not as fixed as you think. Your present choices shape not just your future, but, in some subtle quantum sense, your history as well. The story you tell about how you got here is not written in stone. It is written in probability amplitudes, in quantum superpositions, in the strange half-reality of wave functions that do not collapse until they are observed. The sun sets over Canberra, casting long shadows across the campus of the Australian National University. In the quantum optics laboratory, the equipment is powered down for the night, the lasers allowed to cool, the detectors to rest. But the questions the experiments have raised do not rest, do not power down, do not go quiet. They linger in the minds of the physicists who performed them. who will return tomorrow to push further into the quantum wilderness, to ask new questions of the universe and record whatever answers it chooses to give. What lies ahead is uncertain, which is perhaps appropriate for a field that has made uncertainty a fundamental principle. The experiments will continue, refined and extended, probing deeper into the nature of quantum measurement and the relationship between observer and observed. New results will emerge, challenging or confirming or nuancing what has already been found. And somewhere, perhaps, a new conceptual framework will arise, one that makes sense of all the strangeness, that resolves the puzzles and reconciles the paradoxes. But that framework, if it exists, remains beyond the horizon. For now, we must reckon with what the experiments have shown, with the data as it stands, with the implications as they ramify outward into questions that touch not just physics but philosophy, not just measurement but meaning. And to understand where we stand, we must look more closely at what the experiments actually revealed, at the technical details that transform a conceptual puzzle into an empirical fact. The 2015 Australian experiment, led by Andrew Truscott at the Australian National University, was remarkable not just for what it demonstrated, but for how it demonstrated it. The team chose to work with helium atoms rather than photons, a decision that might seem like a mere technical preference, but carried profound conceptual weight. Photons are strange creatures, particles of light that have no rest mass and travel always at the speed of light. They are in some sense the most quantum of all particles, the ones whose wave-like behaviour was first and most dramatically revealed. But helium atoms are different. They have mass. They have a rest frame. They feel the pull of gravity. They are, in short, more like the everyday objects of classical physics than photons could ever be. And yet, the experiment showed they too exhibit the reality-defying behaviour that Wheeler had predicted. The setup was elegant in its conceptual clarity, even if the technical execution required exquisite precision. The researchers began by trapping helium atoms in a Bose-Einstein condensate, a state of matter that exists only at temperatures barely above absolute zero. In this state, the atoms lose their individual identities, merging into a collective quantum system that can be manipulated with extraordinary control. From this ultra-cold cloud, the experimenters released individual atoms, one at a time, into an apparatus that would subject them to a version of the delayed choice experiment. The atoms fell under the influence of gravity, dropping through the apparatus like tiny stones. But they also passed through a series of laser beams that acted as the equivalent of beam splitters in an optical experiment. The first laser pulse split each atom's wave function into two components, sending them along different paths through the apparatus. These paths diverged, separated, and then, crucially, could be made to recombine, or not, depending on a choice made after the atom had already begun its journey. The second beam splitter, the one at the recombination point, could be switched on or off. If it was on, the two paths would interfere, and the atom's final position would reveal the characteristic wave-like interference pattern. If it was off, the paths would remain separate, and the atom would behave as a particle, arriving at one detector or the other with no interference. The key insight, the feature that made this a delayed choice experiment, was that the decision about whether to switch on the second beam splitter was made after the atom had already passed through the first one, after it had already, according to any classical understanding, committed to travelling along one path or the other. The timing was crucial. The experimenters used a quantum random number generator to decide, at the last possible moment, whether to activate the second beam splitter. The decision was made so late that no signal travelling at the speed of light could have carried information about it back to the atom at the time it passed through the first beam splitter. If the atom had made a definite choice about its path at that earlier moment, if it had decided to go left or right, to take one route or the other, then the later decision about the second beam splitter should have been irrelevant. The atom's nature, particle or wave, should have been fixed by its earlier history, but that is not what the data showed. When the second beam splitter was activated, interference patterns appeared, indicating that the atom had travelled both paths simultaneously as a wave. When it was not activated, no interference appeared, indicating that the atom had travelled one path or the other as a particle. The statistics were unambiguous, repeatable, statistically significant, and yet the decision that determined which behaviour would be observed was made after the atom had already passed the point where, classically speaking, it should have committed to one behaviour or the other. The researchers were careful in their language, as good scientists must be. They did not claim to have proven retrocausality, to have shown that the future literally causes the past. They acknowledged the many possible interpretations, the philosophical complexities, the ways in which different theoretical frameworks could accommodate their results. But they also did not shy away from the strangeness of what they had found. In their published paper, they noted that the experiment weights against models in which the weights that have been deposited have a definite, completed nature independent of the subsequent measurement choice. In other words, the helium atoms did not have a definite history until that history was observed. The Vienna experiment of 2019, conducted by a team led by Philipp Walther at the University of Vienna, pushed the inquiry even further. If the Australian experiment had used massive particles instead of massless photons, the Austrian experiment introduced a new level of complexity: entanglement. The researchers created pairs of entangled photons, particles whose quantum states were correlated in ways that defy classical explanation. When you measure one entangled photon, you instantly affect what can be known about its partner, no matter how far apart they are. Einstein famously called this spooky action at a distance, and it remains one of the most counterintuitive features of quantum mechanics. The Vienna team combined this entanglement with the delayed choice protocol, creating what they called an entanglement swapping delayed choice experiment. The setup was fiendishly complex, involving 4 photons rather than 2, but the conceptual structure was clear. 2 of the photons were sent to distant detectors where they were measured. The other 2 photons were subjected to a measurement that could entangle them, or not, depending on a choice that was made after the first 2 photons had already been detected. If the middle photons were entangled, then the outer photons would become entangled with each other, retroactively. If the middle photons were not entangled, no such correlation would appear. The results confirmed the quantum prediction. The correlations between the outer photons depended on what happened to the middle photons, even though the outer photons were measured first. Once again, a present choice appeared to influence a past outcome, and once again the researchers were careful to note that this did not necessarily prove retrocausality in any simple sense. The correlations could not be used to send signals backward in time, could not be exploited to create paradoxes, could not be leveraged to win lotteries or prevent disasters. The backward influence, if that is what it was subtle, statistical, hidden within the quantum formalism rather than available for exploitation. But the philosophical implications were unavoidable. The experiment demonstrated what the researchers called delayed choice entanglement swapping, a phenomenon in which the decision to entangle or not to entangle particles could be made after those particles had ceased to exist, after they had been absorbed by detectors and converted into electrical signals. The entanglement, it seemed, could be created retroactively, applied to particles that no longer existed in any physical sense. The past, at the quantum level, was malleable in ways that the classical worldview could not accommodate. These results did not emerge from a vacuum. They built on decades of theoretical work, on countless preliminary experiments, on a tradition of careful analysis that stretched back to the founding generation of quantum physics. Niels Bohr had grappled with these questions in the 1930s, debating Einstein about the nature of quantum reality in a series of exchanges that remain landmarks in the philosophy of science. John Bell had sharpened the debate in the 1960s, showing that no theory that preserves local realism can reproduce the predictions of quantum mechanics. Alain Aspect had confirmed Bell's predictions in the 1980s, closing one loophole after another in a series of increasingly precise experiments. And now, in the 2010s, the delayed choice experiments were adding a new dimension to the puzzle, showing that the strangeness of quantum mechanics extended not just across space but across time. The implications reach far beyond the laboratory. If the past is not fixed at the quantum level, what does that mean for the past at larger scales? The atoms in your body are quantum systems. The photons that carry visual information from your surroundings to your eyes are quantum systems. The electrons that carry thoughts through your neurons are quantum systems. Does the quantum malleability of the past somehow propagate upward, affecting the macroscopic world we inhabit? Or does it somehow disappear in the transition from quantum to classical, washed out by decoherence and environmental noise? The answer, as best we can tell, is that the quantum effects are real but subtle, statistical but not exploitable, present but not obvious. The retrocausal influences suggested by the delayed choice experiments do not allow you to change your own past, to send messages to your younger self, to undo decisions you regret. The universe is not so accommodating. But they do suggest that the relationship between past, present and future is more complex than our everyday experience implies, that the arrow of time may be less fundamental than we thought, that the distinction between what has happened and what will happen may be at some deep level a matter of perspective rather than fact. This is a difficult idea to hold in the mind, and physicists have developed various conceptual tools to make sense of it. Some speak of indefinite causal order, a framework in which the question of whether event A causes event B or event B causes event A has no definite answer. Others speak of quantum histories, in which the past is not a single sequence of events, but a superposition of possibilities that collapses into definiteness only when observed. Still others embrace a kind of instrumentalism, treating quantum mechanics as a tool for prediction rather than a description of reality, and therefore treating questions about the true nature of the past as meaningless. Each of these approaches has its advocates and its critics. The debates continue in journals and at conferences, in seminar rooms and on whiteboards, wherever physicists gather to argue about foundations. And the experiments continue as well, pushing into new territory, probing new questions, seeking to distinguish between interpretations that make different predictions about as yet unperformed experiments. One line of research focuses on extending the delayed choice paradigm to increasingly macroscopic systems. If retrocausal effects can be demonstrated with atoms, can they be demonstrated with molecules, with viruses, with microscopic machines? The technical challenges are immense. Larger systems are more prone to decoherence, more difficult to isolate from their environment, more likely to lose their quantum coherence before the experiment can be completed. But the conceptual payoff would be enormous. If delayed choice effects could be demonstrated with systems large enough to be seen under a microscope, it would be much harder to dismiss them as mere artifacts of the quantum realm, irrelevant to the macroscopic world where humans live and think. Another line of research focuses on the connection between delayed choice experiments and the foundations of time itself. Some physicists have suggested that the experiments reveal a deep truth about the nature of time, that they show time to be emergent rather than fundamental, that they hint at a deeper level of reality where the distinction between past, present and future does not exist. This is speculative territory, well beyond what the experiments themselves can prove, but it is territory that some of the best minds in physics are exploring. The philosophical stakes could hardly be higher. If time is emergent, if the flow from past to future is not a fundamental feature of reality but a higher level pattern that arises from more basic ingredients, then our entire understanding of causation, of history, of personal identity, of free will must be reconsidered. The questions are vertiginous, dizzying, impossible to answer with certainty, but they are also exhilarating, offering glimpses of a reality stranger and more wonderful than anything our ancestors could have imagined. Back in the laboratories, the work goes on. The physicists who perform these experiments are, for the most part, not focused on the philosophical implications. They are focused on the next measurement, the next calibration, the next refinement of technique. They are problem solvers, engineers of the invisible, people who take pleasure in making delicate apparatus work and in extracting clean data from noisy systems. The big questions, what does it all mean, are left for quieter moments, for late-night conversations over beer, for the rare occasions when the practical demands of research give way to wonder. But the wonder is never far away. Every physicist who works in this field has felt it, the vertigo that comes from confronting results that seem to violate common sense, that challenge the most basic assumptions about how the world works. They have learned to live with the vertigo, to function despite it, to set it aside when necessary and return to it when possible. It is part of what draws people to this work, the sense that they are exploring territory where the maps run out, where the familiar landmarks of classical physics no longer apply. The map, such as it is, consists of the mathematical formalism of quantum mechanics, the equations that describe how wave functions evolve, how superpositions combine, how measurements collapse probabilities into definite outcomes. This formalism is extraordinarily successful, its predictions confirmed to many decimal places by countless experiments. But the formalism does not tell you what it means. It does not explain why observation plays such a central role, or what an observation is, or why the equations work so well. It gives you the tools to calculate, but leaves you to wonder about the reality behind the calculations. The delayed choice experiments are particularly pointed in this regard. They work exactly as quantum mechanics predicts. The interference patterns appear and disappear on schedule, the correlations fall into place with statistical precision, the equipment behaves as designed. There is no mystery about what happens. The mystery is about what it means. And that mystery is not likely to be resolved by any experiment, no matter how clever or precise. It is a conceptual puzzle, a philosophical puzzle, a puzzle about the nature of explanation itself. Consider what it would mean to truly understand the delayed choice results. It would mean having a picture of reality in which those results make sense, in which they follow naturally from more fundamental principles. Such a picture would have to explain how the past can be influenced by future choices without allowing paradoxes. It would have to account for the role of observation without resorting to mystical notions of consciousness. It would have to be consistent not just with the delayed choice experiments, but with all the other experiments that have probed quantum mechanics, from the original double-slit demonstration to the most recent tests of Bell inequalities. Such a picture does not currently exist. What exists instead is a collection of partial pictures, each illuminating some aspects of the quantum world while leaving others in shadow. The Copenhagen interpretation, with its emphasis on measurement and its refusal to describe reality between measurements. The many worlds interpretation, with its infinite proliferation of parallel branches and its claim that all possibilities are realized. The pilot wave theory, with its hidden particles guided by invisible waves. The transactional interpretation, with its advanced and retarded waves meeting across time. Each has insights to offer, none has won universal acceptance. The situation is not entirely unprecedented in the history of science. There have been other periods when fundamental theories were clear and successful, but their interpretation was murky and contested. The history of Newtonian mechanics includes long debates about the nature of absolute space and time, debates that were not resolved until Einstein swept them away with relativity. The history of thermodynamics includes puzzles about entropy and irreversibility that remain active areas of research today. Science progresses not just by answering questions, but by discovering which questions are meaningful and which are confused. Perhaps the delayed choice experiments are revealing that some of our questions about time and causation are confused, that we are trying to force quantum reality into categories that do not fit. Perhaps a future generation of physicists will look back on our current debates the way we look back on debates about the luminiferous ether, with a mixture of respect for the intelligence involved and relief that we have moved past the confusion. Or perhaps the puzzle will remain, a permanent feature of our understanding of the quantum world, a reminder that reality is under no obligation to be comprehensible. For now, the experiments stand as monuments to human ingenuity and human curiosity. The helium atoms in Canberra, falling through their carefully calibrated apparatus, the entangled photons in Vienna, weaving their correlations across space and time, the data logs recording the outcomes, the statistical patterns emerging from the noise. These are the empirical facts, the foundations on which all interpretation must rest. And the interpretation continues, in papers and books and lectures, in conversations among colleagues and arguments among rivals. The physicists who work on these questions are heirs to a tradition that stretches back to the dawn of quantum mechanics, to Heisenberg and Bohr and Einstein, to the founders who first glimpsed the strangeness at the heart of the atom. They carry forward that tradition not by settling the debates, but by deepening them, by finding new experiments that sharpen old questions, by refusing to accept easy answers when hard answers might be found. The laboratories where this work is done are scattered across the globe, in Canberra and Vienna and a dozen other cities. They're connected not by geography, but by a shared commitment to understanding, by a faith that the universe is comprehensible, even when it is strange, that the quantum mysteries will yield their secrets to patient investigation. This faith is not mystical, but empirical, grounded in the centuries of scientific progress that have brought us from superstition to satellites, from magic to medicine, from speculation to precision. But the faith is also humble. The researchers know that their understanding is incomplete, that their interpretations are provisional, that tomorrow's experiment might overthrow today's theories. They work in the shadow of uncertainty, not just the Heisenberg variety, but the deeper uncertainty of not knowing whether they are on the right track, whether the questions they are asking are the right questions, whether the answers they seek are even possible. This uncertainty is not paralyzing but motivating. It is what makes the work worthwhile, what gives it meaning beyond mere puzzle solving. And so the story continues, open-ended as all good stories are, pointing toward a future that remains to be written. The delayed choice experiments have revealed something profound about the nature of reality, something that defies easy summary and resists comfortable interpretation. They have shown that the past, at least at the quantum level, is not as fixed as we thought, that present choices can shape past outcomes in ways that seem to violate causation, but in fact reveal its deeper structure. The structure they reveal is one that physicists are still struggling to articulate, still reaching for the precise language that will capture what the experiments have shown without overstating or understating their implications. And as with any frontier of knowledge, the path forward is illuminated not just by the experiments themselves, but by the theoretical frameworks that attempt to make sense of them, the mathematical formalisms that translate intuition into rigour, the competing schools of thought that vie for supremacy in the interpretation of quantum mechanics itself. To understand why the delayed choice results have sparked such fierce debate, one must understand that quantum mechanics has never had a single agreed-upon interpretation. From its earliest days, the theory has been a house divided, a magnificent mathematical apparatus that makes predictions of extraordinary precision while offering no consensus on what those predictions mean. The Copenhagen interpretation, associated with Bohr and Heisenberg, dominated the middle decades of the 20th century, teaching generations of physicists to calculate and shut up, as the saying went, to use the formalism without worrying too much about what it signified. But Copenhagen never conquered completely. There were always dissenters, physicists who found its agnosticism intellectually unsatisfying, who demanded a clearer picture of what was really happening behind the equations. David Bohm was one such dissenter. In the early 1950s, while the Copenhagen interpretation reigned supreme, Bohm proposed an alternative that would come to be known as pilot wave theory, or Bohmian mechanics. In this picture, particles always have definite positions, tracing out actual trajectories through space. But those trajectories are guided by a wave function that influences their motion in subtle and non-local ways. The randomness of quantum mechanics, in Bohm's view, arises not from any fundamental indeterminacy, but from our ignorance of the precise initial conditions. The electron going through the double-slit experiment follows a definite path, goes through one slit or the other, but the guiding wave goes through both, and the interference pattern emerges from the way that wave shapes the electron's trajectory. Bohmian mechanics makes exactly the same predictions as standard quantum mechanics. Every experiment that confirms the Copenhagen interpretation also confirms Bohm's theory. The mathematics are different, the ontology is different, the picture of reality is radically different, but the numbers come out the same. This equivalence has been both Bohmian mechanics' greatest strength and its greatest weakness. Strength because it cannot be refuted by experiment, weakness because it cannot be confirmed either. The choice between interpretations becomes a matter of philosophical taste, aesthetic preference, judgments about simplicity and elegance, and explanatory power that resist objective adjudication. And what does Bohmian mechanics say about delayed choice experiments? Here the picture becomes particularly intriguing. In the pilot wave framework, the photon or atom always follows a definite trajectory, passes through one arm of the interferometer or the other. But the guiding wave, the mathematical entity that shapes that trajectory, is influenced by the entire experimental setup, including the settings that will be chosen in the future. This is possible because Bohmian mechanics is explicitly non-local, allows influences to propagate instantaneously across arbitrary distances, even across time in certain formulations. The trajectory the particle takes depends not just on conditions at the moment of the mission, but on the entire four-dimensional configuration of the experiment, including the choice that will be made about whether to observe interference or which path information. This might sound like it solves the retrocausal puzzle, but it merely relocates it. The non-locality of Bohmian mechanics is just as mysterious as the retrocausality it seeks to avoid. How does the guiding wave know about the future choice? How does the influence propagate backward through time, or outside of time altogether? The Bohmian picture trades one mystery for another, arguably an equally deep mystery. leaving the fundamental puzzle intact while changing its surface appearance. Other interpretations face similar challenges. The many worlds interpretation, proposed by Hugh Everett in 1957 and championed by a minority of physicists for decades before gaining broader acceptance in recent years, offers a radically different picture. In this view, every quantum measurement causes the universe to branch into multiple copies, one for each possible outcome. The photon does not go through one slit or the other. It goes through both, and the universe splits to accommodate both possibilities. There is no wave function collapse, no sudden transition from superposition to definite state. The superposition persists, but different branches of the superposition become different branches of reality, each containing observers who see only one outcome and mistakenly believe that outcome to be uniquely real. In the many worlds framework, delayed choice experiments lose some of their mystery. The photon that passes through the apparatus exists in a superposition of having exhibited wave-like and particle-like behavior. When the experimenter makes the delayed choice, the universe branches according to that choice, and each branch contains a consistent history. There is no retrocausality because there is no single past to be affected. The past, like the present and the future, is a branching tree of possibilities, all equally real, all coexisting in the vastness of the quantum multiverse. But this resolution comes at an enormous ontological cost. The many worlds interpretation demands that we accept an infinity of parallel realities, an ever-proliferating ensemble of universes that cannot be observed or tested, but must be posited to maintain the mathematical elegance of the theory. Many physicists find this price too high, prefer to accept the puzzle of delayed choice rather than the extravagance of eternal branching. And the many worlds interpretation has its own difficulties with delayed choice experiments, subtleties involving the timing of branching and the identity of observers across branches that are not fully resolved even among the interpretation's advocates. Then there is the transactional interpretation, proposed by John Cramer in the 1980s, which embraces retrocausality explicitly rather than trying to explain it away. In Cramer's picture, quantum interactions involve an exchange of waves travelling both forward and backward in time. The emitter sends out an offer wave into the future, the absorber sends back a confirmation wave into the past, and the transaction between them determines the outcome of the measurement. This handshake across time, as Cramer calls it, provides a natural framework for understanding delayed choice experiments. The photon's behaviour is determined not just by conditions at the moment of emission, but by the entire transaction, including the absorber that will ultimately detect it, and the choices that will determine the nature of that detection. The transactional interpretation has a small but devoted following among physicists who find its explicit treatment of time more honest than the evasions of other interpretations. But it too faces challenges, both conceptual and technical, questions about how the backward-travelling waves interact with forward-travelling ones, about the mechanism of transaction formation, about the compatibility of the picture with relativistic quantum field theory. No interpretation of quantum mechanics is without its difficulties, its open questions, its uncomfortable implications. This is the nature of the subject, has been its nature since the founding days when Bohr and Einstein argued about what the theory meant even as they agreed about what it predicted. And in recent years, new interpretations have emerged that take the delayed choice results as their starting point, rather than as a puzzle to be accommodated. The retrocausal interpretation, championed by physicists like Hugh Price and Ken Wharton, asks what quantum mechanics would look like if we took seriously the possibility that the future can influence the past. These physicists note that the fundamental equations of physics are time-symmetric, work equally well forward or backward, and argue that our instinctive rejection of retrocausality is a prejudice, a holdover from classical intuitions that quantum mechanics has already shown to be unreliable. In the retrocausal framework, the delayed choice experiments are not paradoxes to be resolved, but clues to be followed. They suggest that quantum mechanics is trying to tell us something about the nature of time, something that our ordinary categories cannot capture. The boundary conditions that determine a quantum system's behaviour are not located solely in the past, but distributed across both past and future. The initial state and the final state together constrain what happens in between, and the correlations that emerge from this dual constraint can mimic retrocausal influence without actually allowing information to travel backward in time. This is a subtle distinction, one that requires careful unpacking. The retrocausal interpretation does not claim that you can send a message to your past self, does not open the door to grandfather paradoxes or timeline alterations. What it claims is more modest and more strange, that the correlations between events at different times can be explained by positing that both the past boundary condition and the future boundary condition play a role in determining what happens. The photon's behaviour in the delayed choice experiment is constrained by both its emission and its eventual detection, and what looks like the present choice affecting the past is actually both events jointly determining the intermediate behaviour. This picture has antecedents in the work of Yakir Aharonov, who developed the two-state vector formalism in which quantum systems are described by both a forward-evolving state from the past and a backward-evolving state from the future. The two states together provide a more complete description than either alone, and experiments designed within this framework have yielded remarkable results. Measurements of quantities that seem impossible, glimpses of quantum properties that standard formulations cannot reveal. Aharonov's work has been controversial, praised by some as a profound new insight into quantum foundations, dismissed by others as mathematical sleight of hand. But the delayed choice experiments lend it a certain credibility, suggest that the two-time approach may be capturing something real about how quantum systems behave. The implications of this work extend beyond the interpretation of specific experiments to fundamental questions about the nature of physical law. If the retrocausal picture is correct, then our usual way of thinking about causation is doubly wrong. Not only do quantum events lack the deterministic causes that classical physics provided, they also lack the temporal ordering that our intuition demands. Causes and effects become entangled across time, influence flows in directions that ordinary language cannot describe, and the very notion of explaining why something happened becomes problematic in ways that philosophers are only beginning to explore. The Vienna experiments of 2019 made these implications vivid and unavoidable. The research team, building on the work done in Canberra 4 years earlier, designed an experiment that pushed the delayed choice paradigm to new extremes. Their apparatus used entangled pairs of photons, particles that share a quantum state across space in such a way that measuring one instantly affects what can be known about the other. By entangling the choice itself with a quantum system, the experimenters created a situation where the decision about whether to observe interference or which path information was not made by a human experimenter, was not even made by a classical random number generator, but was determined by a quantum measurement that had no definite outcome until it occurred. This quantum-controlled switching eliminated another potential loophole in the original delayed choice experiments. One might have worried that some subtle classical process was transmitting information from the experimenter's future choice to the photon's past behaviour, that what looked like retrocausality was actually a failure of randomness, or a hidden correlation in the experimental setup. By making the choice itself quantum, by placing it under the control of a fundamentally random process that could not be predicted even in principle, the Vienna team closed this loophole with devastating finality. The results confirmed what the earlier experiments had suggested. The entangled photons exhibited precisely the behaviour predicted by quantum mechanics, precisely the behaviour that seemed to require the present choice to determine the past outcome. The statistical patterns in the data were not artifacts of experimental design or limitations in randomness. They were genuine features of the quantum world, as real as the laboratory equipment that produced them, as solid as the concrete floors on which that equipment stood. But the Vienna experiments added a new wrinkle to the puzzle. By using entangled photons, they brought together two of the strangest features of quantum mechanics: the delayed choice phenomenon that seemed to require retrocausality, and the entanglement phenomenon that Einstein had called spooky action at distance. The combination was more than the sum of its parts. It suggested that these two forms of quantum strangeness might be aspects of a single, deeper phenomenon, that retrocausality across time and non-locality across space might be different faces of the same underlying reality. This suggestion has profound implications for our understanding of space-time itself. In relativity theory, space and time are unified into a four-dimensional continuum where the distinction between past and future is relative to the observer's motion. Events that are simultaneous for one observer may be sequential for another, and the light cone structure of space-time determines which events can causally influence which. Quantum mechanics has always had an uneasy relationship with this relativistic picture. seemed to require instantaneous influences that violated the spirit, if not the letter, of Einstein's framework. The delayed choice experiments suggest that the tension runs even deeper, that quantum mechanics may require not just non-locality in space, but non-locality in time, influences that propagate not just faster than light, but backward along the time dimension. Some physicists have responded to this suggestion by developing theories that treat space and time on a more equal footing, that allow correlations across time-like separations, just as quantum mechanics allows correlations across space-like ones. These theories are speculative, far from the mainstream, but they are driven by the empirical results that the experiments have provided. The data does not tell us how to interpret it, does not choose between competing theoretical frameworks, but it does constrain what those frameworks can say, does eliminate possibilities that cannot accommodate the observed phenomena. The Vienna laboratory where this work was done is part of a larger complex devoted to quantum optics and quantum information. The researchers there work not just on foundational questions, but on practical applications: quantum computing, quantum cryptography, quantum communication networks that may one day span the globe. The connection between foundations and applications is not coincidental. The strange features of quantum mechanics that the delayed choice experiments probe are the same features that make quantum computers potentially powerful, that enable quantum cryptography to offer security guarantees that classical methods cannot match. Understanding why quantum mechanics is strange is intimately connected to understanding what quantum mechanics can do. The laboratory space itself reflects this dual mission. Optical tables hold experiments in various stages of completion, some probing the foundations of physical reality, others testing components for quantum communication systems. Lasers of various colours cast their beams through carefully aligned optical elements. Detector arrays count photons with nanosecond precision. Computers process data and control experimental parameters, their screens showing real-time results that would have astonished the founders of quantum mechanics, results that even now carry implications that their producers struggle to comprehend. Among those producers are young researchers, graduate students and postdocs, who have chosen to dedicate their careers to questions that may not be answered in their lifetimes. They work long hours in the laboratory, adjusting alignment, calibrating detectors, taking data runs that extend through the night. They discuss results over coffee in the common room, argue about interpretations in seminars that sometimes grow heated, collaborate and compete in the ways that scientific communities always have. They are aware of the history they are part of, the tradition that connects their work to the great debates of the past, but they are focused on the future, on the experiments they hope to do, the discoveries they hope to make, the understanding they hope to achieve. The coffee in the common room is strong, as it tends to be in physics departments around the world, fuel for minds wrestling with problems that resist solution. The conversations range widely, from technical details of experimental design to speculative interpretations that verge on philosophy, from gossip about job openings and grant decisions to earnest debates about what the experiments really mean. The atmosphere is one of intense focus tempered by camaraderie, of competition made bearable by shared purpose, of frustration at the difficulty of the problems balanced by excitement at their depth. And in the background always are the experiments themselves. The apparatus stands ready, the photon source is humming, the detectors waiting to record outcomes that will become data points in a story that humanity has been telling itself since it first looked up at the stars and wondered what they were. The story has grown more complex over the millennia, more precise, more strange. The delayed choice experiments are among its latest chapters, chapters that raise more questions than they answer, that point toward possibilities that our language can barely articulate, that challenge us to think about reality in ways that our brains did not evolve to comprehend. Yet the experiments are also profoundly ordinary. They're conducted by ordinary people using ordinary materials, glass and metal, wires and circuits, photons that obey laws we can write down, even if we cannot fully understand them. The mystery is not located in some exotic realm beyond human access, but right here in equipment we can touch and data we can read, in outcomes that appear on computer screens in perfectly mundane laboratories. This is perhaps the deepest lesson of the delayed choice experiments, that the strange is not far away, not hidden in distant galaxies or locked inside particle accelerators, but present in every photon that crosses the room, in every electron that flows through a wire, in the quantum substrate that underlies the apparent solidity of the everyday world. The researchers who have devoted their lives to understanding this substrate do not think of their work as esoteric or otherworldly. To them, probing the foundations of quantum mechanics is as practical as engineering, as grounded as carpentry. The experiments require real materials, real budgets, real time and effort. The theories require mathematical rigour, logical consistency, respect for the data. The debates require evidence and argument, not just intuition or preference. The work is hard in all the usual ways that work is hard, with the additional difficulty that the subject matter resists ordinary understanding, slips away from intuition like water through fingers. But the difficulty is also the attraction. The physicists who work on these questions are drawn precisely because the questions are hard, because they touch on the deepest issues, because they offer the chance, however slight, of glimpsing something truly fundamental about the nature of existence. They know that most of their efforts will lead to dead ends, that most of their interpretations will prove wrong, that the understanding they seek may be generations away if it is achievable at all, but they persist because the questions matter, because the experiments are possible, because the human drive to understand does not accept boundaries even when those boundaries seem impassable. The drive to understand does not accept boundaries. It never has. From the first human who wondered why the sun rose to the last physicist who will ever calibrate a beam splitter, the impulse is the same: to see, to know, to comprehend what lies beneath the surface of things. And here, in laboratories scattered across continents, in the quiet hours between midnight and dawn when the apparatus runs most cleanly, that drive encounters something that refuses to yield its secrets easily. But perhaps the time has come to ask what secrets have already been revealed. The delayed choice experiments, from Wheeler's thought experiment to the ANU results of 2015 to the Vienna confirmations of 2019, have established something that can no longer be dismissed as philosophical speculation or interpretive preference. They have demonstrated, with the cold precision of photon counts and statistical significance, that the relationship between present choices and past events is not what we assumed it to be. The classical intuition that the past is fixed, determined, settled before we arrive to observe it, cannot survive contact with these results. Something deeper is at work, something that our categories of time and causation and existence struggle to capture. The question that remains is not whether the experiments are real. They are real. The question is what reality itself must be like for these experiments to be possible. Consider, one final time, what happens in a delayed choice quantum eraser. A photon is created. It encounters a beam splitter and, in the quantum mechanical description, enters a superposition of paths. Along each path it passes through a crystal that generates entangled pairs, one photon continuing toward a detector that records interference patterns or their absence, the other diverging toward a set of detectors that can either preserve or destroy the witch path information. The choice of how to measure this second photon, whether to send it to a detector that reveals which path the first photon took, or to a detector that erases that information, determines whether the first photon's arrival shows interference. And this choice can be made after the first photon has already been detected. After. The first photon is already recorded. Its position on the detection screen is already fixed. The choice about the second photon comes later, and yet that later choice determines whether the earlier detection shows wave behavior or particle behavior. This is not a trick of statistics or a quirk of analysis. When the data is sorted according to the outcomes of the later measurements, the pattern is unmistakable. Photons whose partners were measured in a way that preserved witch path information show no interference. Photons whose partners were measured in a way that erased witch path information show clear interference bands. The sorting happens after all the detections are complete, but the patterns were there all along, hidden in the data like a watermark that becomes visible only when you know how to look. What does this mean for the nature of time? The most conservative interpretation is that it means nothing, that quantum correlations are simply different from classical causation, that entanglement creates connections that respect no temporal ordering, and that our confusion arises from trying to impose classical concepts on a quantum world. This interpretation has the virtue of parsimony. It requires no revision of our physical theories, no invocation of signals travelling backward through time, no violation of the causal structures that underlie all of modern physics. The correlations are correlations, not causes. The patterns are patterns, not messages from the future influencing the past. But even this conservative interpretation demands something remarkable. It demands that we abandon the idea that the past has a definite character, independent of how we choose to observe it. The photon's history, whether it went through one slit or both, whether it travelled one path or two, is not determined until the measurement context is complete. And the measurement context is not complete until all the relevant choices have been made, including choices that occur after the photon has been detected. This is not retrocausality in the science fiction sense. No one is sending messages backward through time, rewriting history, killing their own grandfathers. The paradoxes that plague time travel stories do not arise here because the quantum correlations cannot be used to transmit information. The pattern of interference or non-interference appears only when the data is sorted, and that sorting requires information from both measurements, information that can only be combined after both measurements are complete. There is no way to look at the first photon's detection and know, before the second measurement occurs, whether it will turn out to be part of an interference pattern or not. But the absence of information transfer does not eliminate the strangeness. It merely makes the strangeness more subtle, more philosophically troubling, harder to dismiss as mere engineering possibility. The experiments are telling us something about the nature of time and causation and reality, something that persists even when all the practical considerations are accounted for, something that remains when the apparatus is turned off and the physicists go home. The Vienna experiments of 2019 pushed this strangeness further than anyone had pushed it before, by using gravitational time dilation to create situations where the temporal ordering of events became observer-dependent. They demonstrated that the delayed choice phenomenon is not tied to any particular reference frame, any particular clock, any particular definition of before and after. The correlations persist regardless of how you slice up space-time, regardless of whether you consider one measurement to precede the other, or the other way around. The quantum world, it seems, does not care about our conventions for ordering events in time. It cares only about the correlations, the patterns, the relationships that emerge when all the pieces are considered together. This is what the experiments have revealed. Not time travel, not retrocausality in the simple sense, but something perhaps more profound. A universe in which the flow of time, the fixity of the past, the separation of cause and effect are not as fundamental as we believed. These things emerge in some sense from a deeper reality where they do not apply, where the distinctions we take for granted dissolve into a quantum substrate that our minds were never designed to comprehend. And yet we comprehend it, partially, imperfectly, through the mediation of mathematics and experiment. The equations of quantum mechanics describe this substrate with extraordinary precision. The experiments confirm its predictions with extraordinary reliability. We cannot visualize it, cannot imagine it in the way we imagine chairs and tables and the passage of days, but we can calculate it, test it, use it to build technologies that work. The gap between what we can compute and what we can understand is one of the defining features of modern physics, a gap that the delayed choice experiments make vivid and unavoidable. There is a temptation, when confronted with such results, to retreat into instrumentalism, to say that the equations are just tools for predicting observations, and that questions about the underlying reality are meaningless or unanswerable. Many physicists adopt this stance, at least in their professional work. It allows them to use quantum mechanics without being troubled by its implications, to calculate and experiment without worrying about whether the calculations describe something real. The approach is pragmatic, defensible, productive in its way, but it is not satisfying. The human mind, or at least some human minds, cannot rest content with tools and predictions. They want to know what is really happening, what the world is really like, what the experiments are really telling us about the nature of existence. This desire may be naive, may be a relic of evolutionary pressures that have no relevance to fundamental physics, may be a source of confusion rather than insight. But it is also the desire that drives science forward, that motivates the experiments in the first place, that keeps physicists working late into the night when they could be home with their families or pursuing more lucrative careers. The desire to understand is not a weakness to be overcome, but a strength to be cultivated, even when, especially when, understanding seems impossibly distant. What then should we make of the delayed choice results? What understanding can we extract from experiments that seem to defy our most basic intuitions about the world? Perhaps the first thing to understand is that our intuitions are not neutral. They are the product of evolution, shaped by the demands of survival in a world of medium-sized objects moving at medium speeds across medium distances. They're adapted to tracking predators and prey, to navigating landscapes and social hierarchies, to predicting the behaviour of things that behave classically. They have no reason to be adapted to the quantum world, which plays no role in the survival challenges that shaped our ancestors. When our intuitions fail in the face of quantum phenomena, this is not a defect in quantum mechanics, but a defect, or rather, a limitation, in our intuitions. The second thing to understand is that the quantum world is not a separate realm, distant and exotic, but the foundation of the ordinary world we inhabit every day. The chair you sit on, the air you breathe, the neurons firing in your brain as you process these words, all of it is made of quantum stuff, governed by quantum laws, exhibiting quantum behaviour that only appears classical because of the statistical averaging of countless quantum events. The solidity of matter, the flow of time, the apparent determinism of the macroscopic world, these are emergent properties, patterns that arise from the underlying quantum chaos in the same way that the wetness of water arises from the behaviour of individual molecules that are not themselves wet. The delayed choice experiments reveal this underlying chaos, or rather, they reveal that chaos is the wrong word, that the quantum world is not chaotic but precise, not random but correlated in ways that transcend our categories of order and disorder. The correlations between entangled particles are not the result of hidden variables, not the result of signals passing between them, not the result of any mechanism that our classical minds can imagine. They are simply there, fundamental features of reality that must be accepted rather than explained, starting points rather than conclusions. And among these correlations are the ones that the delayed choice experiments exploit, the ones that seem to reach across time as easily as they reach across space, the ones that make the boundary between past and future as permeable as the boundary between here and there. This is the climax of our story, the point toward which all the experiments and theories and debates have been leading. The universe, as revealed by quantum mechanics, does not respect the boundaries that we impose upon it. It does not care that we think the past should be fixed and the future open. It does not care that we think causes should precede effects. It does not care that we think reality should exist independently of how we choose to observe it. The universe simply does what it does, exhibits the correlations it exhibits, and leaves us to make sense of it as best we can. The physicists who performed the NU experiment in 2015, who saw the pattern of interference emerge from data that should have been random, who watched the analysis confirm what Wheeler had predicted decades before, they felt something in that moment. Not triumph, exactly. Not satisfaction. Something closer to awe. The awe that comes from glimpsing something vast and strange. Something that resists comprehension even as it yields to investigation. They had confirmed a result, added a data point to the great human project of understanding. But they had also confronted a mystery, a reminder that the world is deeper and stranger than any theory can fully capture. The physicists in Vienna who extended the experiments into the relativistic regime, who used atomic clocks and gravitational time dilation to probe the quantum relativistic boundary, felt something similar. They were not solving the mystery. No one has solved it, no one may ever solve it. They were deepening it, showing that the strangeness persists even when you account for the most sophisticated physical theories, even when you consider reference frames and proper times and the curvature of space-time itself. The mystery is not a gap in our knowledge that will be filled by future discoveries. It may be a permanent feature of the relationship between mind and world, a limit on what creatures like us can know about a universe like this. But limits are not stopping points. They are challenges. The history of physics is a history of limits overcome, of impossibilities that turned out to be merely difficult, of mysteries that yielded to new methods and new ideas. The delayed choice experiments may seem to reveal something irreducibly strange about the quantum world, but future physicists may find ways to make it comprehensible, to fold it into a larger framework that makes sense of what now seems senseless. Or they may not. The universe is under no obligation to be comprehensible to beings who evolved to hunt on the African savannah. Either way, the experiments matter. They matter because they tell us something true about the world, something that must be accounted for by any theory that claims to describe reality. They matter because they challenge our assumptions, force us to think more carefully, push us to question ideas we had taken for granted. They matter because they are beautiful in the way that all deep science is beautiful, elegant and surprising and resistant to easy summary. They matter because they connect the work of modern laboratories to the great traditions of human inquiry, the same traditions that produce geometry and astronomy, and the theory of evolution, and the periodic table, and all the other achievements that make our species something more than clever apes. The coffee in the common room has grown cold. The conversations have wound down. The physicists have returned to their apartments or their offices, to their families or their calculations, to the ordinary lives that they lead alongside their extraordinary work. The apparatus stands silent now, the photon source is dormant, the detectors no longer counting arrivals. Tomorrow or next week or next month, the experiments will resume, and new data will be collected, and new analyses will be performed, and the slow accumulation of knowledge will continue. But for now, in the quiet of the laboratory, there is only the hum of the climate control and the faint glow of indicator lights, the stillness of equipment waiting to be used. If you stood in this room, in the darkness between experiments, you would see nothing remarkable, just the ordinary clutter of a working lab, cables and mounts and boxes of supplies. You would hear nothing remarkable, just the background noise of a building that never quite sleeps. You would smell nothing remarkable, just the faint chemical tang that hangs in laboratories everywhere. And yet everything in this room, every atom of every object, every photon that bounces off surfaces and enters your eyes, every electron that flows through the circuits keeping the equipment alive, all of it is part of the quantum world, subject to the same laws that the delayed choice experiments probe, exhibiting the same strange behaviour that seems to collapse the boundary between past and future. The mystery is not confined to the experimental apparatus. The mystery is everywhere. The experiment merely makes it visible, brings it into focus, forces us to confront what we would otherwise ignore. This is what John Wheeler understood when he proposed his thought experiment, what Alain Aspect glimpsed in the Bell test results, what the teams in Australia and Austria confirmed with their careful measurements. The strangeness is not an artifact of quantum mechanics, not a defect in our theories, not a puzzle to be solved and then forgotten. The strangeness is the message. The universe is telling us something about itself, something that we have not yet learned to hear clearly, something that may take generations or centuries to fully absorb. We are not separate from the world we observe. Our choices matter, not just for the future we will inhabit, but for the past we thought was settled. The arrow of time, which seems so obvious and inevitable, may be an emergent phenomenon rather than a fundamental feature of reality. The distinction between here and there, between now and then, between observer and observed, these may be useful approximations rather than deep truths, scaffolding that helps us navigate a world we do not fully understand. The delayed choice experiments have not answered the great questions about the nature of time and causation and reality. They have sharpened those questions, made them more urgent, demonstrated that they cannot be avoided or dismissed. The experiments are invitations to think more deeply, to question more persistently, to hold our intuitions more lightly. They are glimpses through a keyhole into a room we have not yet entered, hints of a reality that exceeds our current comprehension. And this, in the end, is what science offers. Not certainty, but glimpses, not answers, but better questions. Not the comfort of understanding, but the exhilaration of standing at the edge of the unknown and looking out into the vast territory that remains to be explored. The physicists who have devoted their lives to quantum foundations are not foolish enough to think they have solved the mysteries. They are wise enough to know that the mysteries are worth pursuing, that the pursuit itself has value, that even partial understanding is better than comfortable ignorance. The equipment will run again tomorrow. The photons will stream through their channels. The detectors will count their arrivals. The data will accumulate in computer files waiting to be analysed. Somewhere in that data may be hints of something new, something unexpected, something that will force yet another revision of our picture of the world. Or the data may simply confirm what is already known, add another brick to the edifice of established physics, contribute to the slow, patient work of understanding that has occupied the best human minds for centuries. Either way, the work continues. Either way, the questions persist. Either way, the universe keeps its secrets even as it reveals them, offers answers that generate new questions, presents mysteries that deepen even as they yield to investigation. The lights in the laboratory dim automatically as the night deepens. The apparatus waits in darkness, ready for tomorrow's experiments. And in that waiting, in that silence, in that ordinary room filled with extraordinary questions, the boundary between past and future grows thin, becomes permeable, reveals itself as something other than what we assumed. We thought we knew what time was. We thought we knew how causes and effects related. We thought we knew the difference between what has happened and what will happen. The delayed choice experiments have shown us that we knew less than we believed, that the world is stranger than we imagined, that the questions go deeper than we suspected. The photon does not ask whether we are ready to understand its behaviour. It simply behaves according to laws we have written, but not comprehended. The universe does not wait for us to catch up. It simply is what it is, and we are left to make of it what we can, to ask our questions and perform our experiments and argue our interpretations, to add our small contributions to the great human effort to understand. In the end, what the experiments reveal is not an answer, but an invitation, to keep looking, to keep asking, to keep wondering. The mystery that began with Wheeler's thought experiment and continued through Aspect's tests and the ANU confirmation and the Vienna extensions, that mystery remains open, unresolved, beckoning. Perhaps that is as it should be. Perhaps the deepest truths are not the ones we solve, but the ones we learn to live with, the ones that shape our thinking without ever fully yielding to it. Perhaps the proper response to the delayed choice experiments is not frustration at their strangeness, but gratitude for the glimpse they offer, the window they open onto a reality that exceeds our comprehension but not our curiosity. The past and the future meet in the present moment of observation, and in that meeting something happens that our words cannot quite capture, our mathematics can only describe, our experiments can only reveal in fragments. The work continues as it must, as it always has. And somewhere in a laboratory, waiting for tomorrow's experiments, the apparatus stands ready to ask the universe its questions once more, to receive answers that will generate new mysteries, to continue the endless conversation between mind and world that is the deepest project of the human species. Outside, the stars wheel overhead, indifferent to our questions, burning according to physics we mostly understand. But every photon from those distant suns, every quantum of light that has travelled for millions of years to reach our eyes, carries the same strangeness that the experiments have revealed. The mystery is not local, it is cosmic, woven into the fabric of everything that is, present in every interaction, every measurement, every moment of existence. We are part of that fabric, observers entangled with what we observe, participants in a reality we did not choose but cannot escape. The delayed choice experiments have shown us that our participation matters, that our choices echo backward as well as forward, that the boundary between observer and observed is not as solid as we thought. The laboratory is quiet now, but it will not stay quiet. Tomorrow, the work begins again, and the day after, and the day after that. The great project continues, generation after generation, question after question, glimpse after glimpse. And in that continuing, in that persistence, in that refusal to accept mystery as defeat, lies something essential about what it means to be human. To stand at the edge of understanding, to reach for what cannot quite be grasped, to ask questions that may never be fully answered. The universe does not owe us comprehension, but it has given us the capacity to wonder, and that perhaps is gift enough.